mij altijd op nul. Okay, good evening everybody. Everybody here, everybody online. Welcome at the Innovation Café. I'm improvising. Today we have a very esteemed speaker, a person that I know quite well. I've known him for almost 20 years now. So that's already a long time. And for me that's easy because then I don't have to study from a paper what this person is all about. Johan Gielis. And Johan Gielis is the discoverer of something called the Superformula. And that formula has so many applications and implications in both a visual field, in a scientific field. And he's here to tell us all about it. And enjoy the talk.
Yeah. Thank you. Welcome to this talk about the Superformula. This is one of the iconic shapes made with that formula. So, but I have to go back a few slides. So, well, my work is used all over the world, and it shows up even in, let's say, art collections somewhere. So on the upper right, Superformula with Pythagoras and pi. So it's a bit, fundamental in science and technology and mathematics. So, first of all, I would like you to imagine a few things. Let's start from this square. Let's start from this one. And you have 4 points, and you try to inflate it with air, and then you follow this route. Or you can have these 4 points attached and inflate it further, and you can imagine that the shapes grow like this. But you can also make it immediately into a pentagon or a hexagon or a 2-angle or a 1-angle. And all these shapes just differ in a few numbers. That's all. And that's why we call it the Superformula, because starting from the square and the circle, this is called a supercircle. And because I generalized the supercircles with symmetry 4 into any symmetry, I coined it the Superformula. So, but shapes like this, they just differ in a few numbers from classical circles and squares. And the fantastic thing about it is that it's a continuous transformation. It's just with sliders, few numbers, and also in 3D we can make fantastic shapes like that. My talk will be a bit special. Normally I don't give too many talks to general public, but let's say I want to give a bit of background, how we got there in the end. Then I will talk about if you have a mathematical formula, what can you do with it? First, you can use it to put in some numbers. You can generate images. You can generate sounds. Secondly, analysis. You scan leaves, you scan seeds, you scan or you get sounds inside. How do you transform it back into numbers? And then optimization. So if you have a formula, how can you think about doing things better, faster, cheaper, and things like that. So synthesis, analysis, and optimization. And then finally, I will give a bit on how I see the developments in the future. So my background is actually not in mathematics. My background is botany and horticulture. So I was for 25 years, I was in plant biotechnology. I developed methods for fast propagation of bamboo. But bamboo is a very, very important plant. Almost 1 billion people use it in their daily lives or live depending on the bamboos. And it's mostly the poor people in the... So I think with our methodology, we have something north of 30 million bamboos produced for plantations and so on. So, but then after I discovered the Superformula, thought about it, I left and did other things. So, but this is being continued. But bamboo is important. Why? Because I thought about bamboo all the time. Why is it so strong? Why is it so special? And so on. It's just a grass, but it can grow 30 meters tall. It can withstand tropical storms. It bends, but it doesn't break, and things like that. So I was very interested in understanding it from an engineering point of view. What's so special? But then I came across mathematical text, general mathematics book, and it showed shapes like this. and it's in between a circle and a square. Remember, if you inflate a circle into a kind of super circle, and I saw these shapes and I say, well, I know this because there are, well, 99% of the bamboos have cylindrical stems, but some bamboos in China have square stems. I will show a few slides, but I have a table there, and there's many shells and things that you can see and feel. Just not believe the images only, but a look and feel over there. And that's where it started. So a square bamboo, and I found that this is a very, very easy way to do it mathematically. And I'll show you. I'm not going to talk too much about mathematics. That would spoil the fun, I think. And then, okay. So, but I was only thinking about squares and so on. But what I had in mind, well, you don't only have squares, you have triangles, you have pentagons, you have these shapes, you have shapes like this, you have all these leaves. This is DNA and enzymes, they also have a regularity. Is there some kind of way to capture the geometric essence of all these shapes? How can you describe them? And well, I could already do a lot of things with the squares, and, but what I was trying to figure out, can I do something? Can I generalize it to encompass triangles and hexagons and so on? And yes, that turned out to be, and this is the only mathematics I'm going to show, but I wanted to show it because this is the Pythagorean theorem and the circle. Yeah? But here you have squares, Pythagorean theorem, and here Gabriel Amé generalized this for some number. And with this sum number, you can inflate a square into a circle and to a super circle. Just one number. And you can also do, this is a obituary written with a student of mine, and then I generalized it into this way. It looks strange, but what is important is actually this m divided by 4. By only doing that, I could, if I fill in 4, I have all the squares. If I fill in 5, I have all the pentagons and the starfish. And I could also use this as a transformation onto some spiral or something. Yeah? And this I called Superformula, and later mathematicians called it Gielis Transformation. And yeah, they asked me not to argue with them. So what can they do? So as I said, the imagine part. So if you start from a square, you can do all this. We knew that. Starting from a triangle, from a hexagon, pentagon. And what interested me most was natural shapes. So if you look at a shape like this, or if you look at many shapes in nature, they're triangular, pentagonal, hexagonal, starfish like that. But I will show some examples that starfish, we have images in our mind of starfish and snowflakes, but they're not always what they seem. We think in archetypes, but our nature is so inventive, unbelievable. What is interesting is you can also modify, let's say, logarithmic spirals like you see in mollusks, and you can also modify flowers. And this is very interesting because I'm a botanist, and now I work in antenna technology with waves, but mathematically it's just the same. But flowers are nicer to look at. I don't see waves in electromagnetics, so that's, but it's actually completely the same. So I'm the botanist inside antenna company, so doing the same math. What was interesting then, and that was started in 2001, I wrote a book about it. You see these shapes already in nature. Flowers, eggs, diatoms, square stems. Flowers are developing with four petals. Also fossils or spirals like this. And it's a uniform description of a range of shapes. So before we thought a circle and a square and a triangle and a starfish all different. You can say, well, a pentagon and a starfish have each 5 arms or 5 angles. But that was about it. For the rest, it was all different. And now we have a continuum of shapes, all the same, one happy family. And as I showed in the diagram, it's not that much different from Pythagoras and the circle. And even some pretty complicated shapes are relatively easy to make. So I didn't make these. So many of the things I saw are made by let's say, other scientists or other, let's say, graphic designers around the world. But I like the images so much that I like to show them. So leaves like that or like that. So again, we can make waves like that as well and sound. So if you read about, let's say, nature and shells, you always come to the logarithmic spiral and Fibonacci and so on and so forth, the Nautilus. And you see this kind of spiraling in snails. Snails grow on land, have nothing to worry about, they can grow all day. But actually mollusks in the sea, they have to deal with tides and so on and so forth. So their growth is a bit anisotropic. So they grow like this, and there are many shells as an example there. And so most of these things can be done as thinking about the logarithmic spiral with my transformation on it. So it's a very wide range of shapes that can be done like this. So when I published my paper in the American Journal of Botany in 2003, a botanical paper, but it got worldwide attention at that point. And it even ended up in Nature. So mats get into shape. Is it a starfish? Is it an orchid? No, it's Superformula. And it was published in the American Journal of Botany, which was then Carl Nicholas, who was the editor-in-chief. I was also, this appeared on another website, a mathematical website. I visited Ulf Greenander, we talked about it, and Tom Gerards later became my PhD advisor in Radboud Universiteit. And yeah, we thought from the beginning there were a huge amount of possibilities. And that turned out to be true. So I will talk a bit about this later, but the original paper in the American Journal of Botany has been cited more than 500 times, 600 times in a minute, which means that it's one of the top 1 or top 2 cited papers of all time. And the interesting thing, as I will show later, is not only in botany, not even in botany, it's all fields of technology, psychology, mathematics, and so on. Anyway, as I said, there's a lot to talk about, but I wanted to divide it into 3 sections. If you have a formula, what can you do with it? You can type in numbers and get sounds or get whatever. And this is the synthesis part. I will just show 3 examples: supergraphics, antenna company, and mechanics and design. Now, supergraphics was something special because back 20 years ago, we asked ourselves, what can you do if you have a formula? Are you going to make a drawing software and compete for space in the shop with Illustrator and so on? And we decided, with Albert also, to do something radically different. So we wanted to do something radically different to position ourselves, and we called it supergraphics. So, and we were thinking about what is supergraphics, what is computer graphics in general. So at that time, early 2000s, computer graphics was well developed. You had all kinds of fantastic cinema, 4D and so on, and Illustrator. You could do so many things already. But before that, before the 70s, before all this technology came into the computer, you could try to do what you have in mind. You had some lines and arcs and another line, and it was not easy. So the old AutoCAD. So, but the second phase, from when you had the Béziers and the NURBS, as you have in these things, you can do anything you can think of. And that idea is all these animation movies, all these documentaries, all this AI, and so on. You can do anything you can think of, and fantastic movies. Huh? And then our question was, is there a next phase? Huh? And then, I don't know who, it was in a brainstorm with Albert and a few others. We thought, well, actually, there's so much we cannot think of ourselves. So, and in that simple sentence, the computer became from a computing device to compute what you wanted it to compute into a creative sparring partner. And that was, we had a lot of success at that time in SIGGRAPH and so on. So. But it was commercially, it was a bit less of a success, but I will show you some examples because, so what you could do in Illustrator, you could have a drop-down menu of a few shapes. And if you have antenna software or if you have CAD/CAM, you can have a cylinder and a few shapes, but not too many. And we had software that spit out shapes as if it was nothing. So by pushing a few buttons, you could generate hundreds of shapes. The wildest shapes never existed before. All new shapes, they never existed before, just came out. And Albert once said to me, well, actually, maybe it's not that shape that I need, but maybe it can inspire me in my next project. So it's a creative sparring partner. The computer becomes a creative sparring partner. Also, we did some tests, for example, how good does it work? For example, if you wanted to make from an illustrator shape something like this, I don't know how it is now, but 20 years ago you had to go through a lot of steps, and with us it sprang out of the computer in a millisecond or so. And there were even shapes that Illustrator or any of these things could not make at all. And so our software could make these things. So we called it Super Graphics, Illustrator Shapes, a lot of handlings and so on, and they just jumped out of the computer. So this is another view, and as I said, all unique shapes. But for example, if you wanted to design a logo for something, and you went with a logo to somebody, to your client, and he said, well, I don't like it, then you push the button and you get 100 variations on a theme. And this is something, one of my favorite things, this was made by Albert. We called it Future Fossil. So we also had a 3D shape explorer, as we called it. And actually we had software in boxes like this. And so Albert just played around for, so I think it was 1 hour. He generated 400 shapes in 1 hour, and then selected 16. And his idea was, how do we tell this story? How do we tell the story of something, really foundational and groundbreaking? And he said, well, my uncle collects butterflies. So collects butterflies and puts them with a pin. And we're going to do the same. I go into a mathematical universe. I capture a few shapes that I like. And we write the names, in this case, the numbers associated with that shape. So an iconic image. And later we found that the shape like this occurred in the fossil record. There are fossils that have shapes like this. So I just visited, yeah?
Those numbers are, the numbers built in the formula?
Yes. But I'll show you some examples later. So, and then this was in a magazine, so another of Albert's, these are all Albert stuff. So this was a design for Business Angel. Oh, just coming back. So he did this in 1 hour, and it was rendered overnight in Cinema 4D. So, and the idea was, if I have to come up with 3 or 4 new shapes, that's hardly possible. So maybe the first shape is new, but the second shape will be a bit different, and haven't I seen it somewhere else? You can guarantee that all these shapes are unique. So this was like 24 hours back then, you told me, and you could not do that in any possible way in a reasonable time. So even like that, so it disappeared. Impossible simply does not exist. So Business Angel, just a few shapes put together, and it was done. It was a lot of work, but it was done fast. So good. And also crazy shapes like this. So, and then actually we were, I think at Drupa in Germany, and we were some guys from the printing industries of America found us. And eventually in 2004, we got the Intertech Technology Award for Innovative Excellence. Because what really impresses them was the time it saves designers. Now you have to think back 20 years, though, everybody was shifting in America, all the creative jobs to India, and all the designers were trained to write invoices like that. So, and saving time in design process and graphical arts was very important. And in the jury report, it says brilliant, off the charts in terms of innovation. I have to say so it's good to be, it's a nice quote, off the charts in terms of innovation, but it's a dangerous one because it's too far out. We found it. But as a Albert's work also appeared in Computer Graphics World, and he said, well, I could not have done this in a reasonable time. And the product manager of Maxon Cinema 4D says, well, I can make shapes I could never make before in just a few moments. And this shows a bit what it can do. As you can do, and I don't know, I put it somewhere on the slide. I think it was the previous slide. So this was 20 years before Dal-E and all these kind of image generators. So, but what was very important is that, and I think that's a problem with OpenAI, so we left the choice to the designer. So the computer was a creative sparring partner, but we did not force someone to choose. So the designers like Albert and so on, they were in charge. And I think that's something very important to keep in mind also about ChatGPT and so on, and OpenAI. So the second thing, so in 2013, in 2009, I came into contact with a mathematician antenna engineer, Italian Diego Caratelli. And in 2010, we started Antenna Company. We are located in Eindhoven. We are 37 people, I think, with offices in Taiwan, China, and California. Here in the high-tech campus, we have something like 30 people working on design of antennas. And again, this is how do we measure antennas? But again, from a geometrical point of view, everything is an antenna. If you have something outside and inside, whether it's your skin or whether it's a flower that wants to attract pollinators, they have an antenna function. And again, for me, it's irrelevant if we look at flowers or if we look at antennas. So this is from our website. We do IoT antennas, we do Wi-Fi antennas, we do millimeter wave antennas, but it's all inspired by nature. So again, from bamboo to antennas and wireless communication, connecting everything. So I think we shipped over 12 million antenna systems so far. So we're doing well. Economies, if you look at Philips, economy is not so good. Everybody's laying off people, but we hope to manage through the downturn of economy and go back. But we sell to the Ciscos of this world, the real big ones. Okay, so here are some examples. For example, this was our first product, and this was for antennas for outdoors, and they were like that because they all have antennas like this. And we had actually egg antennas. So the size of the whole product could be reduced to this size, which was a success, of course, because packaging, shipping, maintenance, all becomes much easier in this way. These are other types of antennas. This is, for example, a filter to normally, if you go smaller, lower in frequencies, then everything gets bigger. If you go higher in frequencies, everything goes smaller. But by taking the shape, we can keep the same size and go down or up in frequency. For example, this is an isolation, and that's very interesting because this belongs to a class of families which is called metamaterials, and they are metamaterials. If you look at a fish in the water, you see it like this. With metamaterials, you can see behind the corner. So this is, we can use the super shapes as metamaterial. And I am working with colleagues in diatoms, and they are natural metamaterials. It was always thought that these were only man-made materials, but they're also, we find them also in nature. Diatoms are a fantastic specimen. They provide 20% of the oxygen of every fifth breath that we take is oxygen produced by diatoms. Metamaterial. So that's a fantastic field to optimize things. So, and the third thing is just mechanics. So if you do CAD/CAM and you design cars and so on, it's always a tedious job. And then if you have to transfer it to a file, or if you have to transport it, everything gets caught up in triangles. You have to triangulate if you want to compute stresses on things. Everything has to be triangulated, and you have to compute it with finite elements, as they call it. And so in each node you compute stresses. So here we have the advantage, and this was from a friend of mine in France, Johan. He did his PhD thesis on the Superformula. This consists of 256 shapes, and it's one equation. On top of that, we not only describe the outline, but everything inside can also be defined. So a field which could be a stress field or a heat distribution is also defined immediately. So fractals can also be made in this way. But again, one equation, all this is one equation. So it's a quite elaborate equation, but it's a very simple one. So, and that is called mesh-free modeling. So you don't have to mesh things, you just can compute every, what they call boundary value problem on the domain and inside the domain itself. So this is a field completely in, let's say, in evolution. We are still working on the mathematics behind it, but I expect in the next 10, 20 years that we have solutions for that. So then the second part is analysis. So yes, it looks like a Superformula, but how do you prove it? So, and how do you prove scientifically that it's a good methodology? Well, that's another part. And this is actually, this summarizes it, more than 40,000 natural shapes, starfish, seeds of plants, leaves of different plants, tree rings, the shape of bamboo stems, all Superformula. And that's interesting for a reason I will talk later, because all our methods in science are based on circles and straight lines, but we don't find any circles. We only find super ellipses. So something's wrong. And so less is more. So if we think a circle, we can define all circles just by their radius. Position, they can be leaving around position, small circles, big circles. One radius defines all circles. What can we do with two parameters? So for example, we can define all bamboo leaves in the world. One for size and one for shape. That's all we need. So just to show how strong it is. And I call this, now we call this the simplified Gielis equation, because you need only, of the 6 parameters, you need only 2. Yeah, well, actually the beginning was in 1993, square bamboos, but until 2020 we had not looked at it in scientific detail. And then our friends, my friends in China, started to cut down square bamboos, and they took 750 sections of cones like this, and it all fitted well. So with the nice statistics, I think there are, on what I say on this 40,000, there are something like 40 papers published in scientific literature. You can all look it up. And this confirms the original conjecture, and it also shows that it's a scientific methodology. That is very important, not only an analogy, it looks like it, but it's really strong scientific methodology. And of course, you could use it for starfish, and as I said, this is the archetypical shape of starfish, but there are many what they call cookie starfish. There are some there, and starfish like this, which have short arms, but they exist. Nature is very inventive. They experiment with all. These are diatoms, but these are actually not real diatoms. They're digital diatoms. So somebody took them and looked at them. So he has software, and he can scan a real diatom and put it back into shapes like this. Fantastic. Also educationally very important. These are triangular fruits, also a very good fit. And what was most astonishing was that actually, if you look at tree rings of conifers, softwoods, you see really squarish stems. They're not round. And actually, that's it's very amazing. Even in the softwoods where we think it's round, it's a circle. It's not a circle. It's provably not a circle. So, and that's one of the most fascinating things. There are some circular things, but they're very rare in nature. So, if we look at starfish, so if we analyze starfish and we use this formula, for example, you could think of these are all may all be different species. But, for example, they could be different ecotypes living in so far away. So and you could study, maybe it's a development from something very small to a larger one. So you could use it in all these kind of ways of studying natural shapes. So avian eggs. For example, this was the existing model, and this is our model. So much better for almost all the avian eggs. Now we're looking at insect eggs, and so we go step by step. You cannot do everything at once. So what is very important in the past 10 years has been really to focus on the technology, to prove that you can build a company from it and you can make profit from it, and also to make it into a scientific methodology. Not it looks like it, no, it is these numbers, and the models are much simpler than if we would do it with circles. So then we come to the third part, optimization. You have a formula, but how can you think about doing things better? And I have just a few examples. For example, first of all, you have to think you need only a few parameters. And when we thought about with Bert, Bert Berings, how are we going to generalize this in 3D? And then we thought, well, if you have a sphere, and you cut it like this, and you cut it like this, you have two circles. So you have a circle that turns around a circle. Now, then it becomes easy, because you take a cube, a square, and a square. You take a cone, a circle, and a triangle. And that's only what you need. This is one section, and this is the other. For example, you have a pentagon and a rectangle. Or so you have a hexagon and a rectangle. And so you have something like a 6 hexagon also, and a rhomb, or a square, or something like a 1 angle. And it doesn't add complexity. The complexity is additive. So if you have, in this case, you have 4 numbers, then you have 8, 4 plus 4. But you cannot only you can also make the shape making a bigger thing, and then you can make everything toroidal, you can make everything go into 3D. And you can make the wildest shapes. We use this from Shape Explorer, and this is, so it's virtually completely unlimited, but it does not become more complex. So, we did some experiments, and so in the software we built back in 2004, making a race car, toy race car, making a toy plane and so on. So, and all these shapes were less than 4,000 bytes. Just imagine if you would do that in a CAD/CAM program, you're talking about mega gigabytes. Less than this, I think this was, yeah, there were 20 parts in the toy race car, and it was something like maybe 800 bytes or so. The important lesson is your technology can be fantastic, but industry is very conservative in general, so that's why we started very carefully with antennas. So, and not with everything at once, but at certain point it will surface. Another thing is speed of computation. We use the algorithms using the Superformula in antenna company, and we compute much faster. And I take 2 examples. For example, an antenna design, a lens antenna, like the one I showed in the beginning with the half eggs. To compute it in for 60 gigahertz radar and so on. So it took, in the normal way, 17,400 seconds, a lot. With us it was 3 times less. Still a lot, but it was done on a personal computer. So, the memory required, we only required a quarter of the RAM memory needed to do the full analysis. In acoustics, to compute waves traveling into liquid, slow and fast waves. In the finite element, you remember I talked about finite elements. So 1800 seconds and 20 seconds, that's all published. And these are the numbers we got. It's really a fantastic jump. It's really this beyond every a laptop. It was done on a laptop. So your government makes your dollars or you make your euros at work. So since 2016, they use the Superformula for procurement. So And you can look up on their website, you can look at tool Superformula, Belastingdienst procurement. And they used it, and it was engineer Hans Kuiper who started doing this. He came from the the NS. He was in procurement, and he developed he used a simplified simplified form of my formula. And after evaluating, after 5 years, they evaluated, and they evaluated something like 200 procurement things, let's say different instances, where they asked what's your price and what quality can you give. On the average, 30% sharper prices, less cost for your government in that case, and 20% better quality. So that's fantastic. This is not about something incremental. And this is not 1%. No, we're talking about 2 times better, so 10 times better. And Hans Kuiper also used also the Superformula to redo some images, iconic images from lips. Another thing is, if we look at nature, something strange happens. We think a tree is subject to all kinds of stresses throughout the year, wind, rain, biotic, attacked by diseases and so on. And we want to, if we think about optimization, we think there's 20, 40, 100 dimensions in data science. It's normal these days, and so they talk about dimension. And actually the solution that trees use is only 2 dimensions. They don't have to deal with 20 dimensions. They do it in a simple 2-dimensional space. And so if you have a tree ring in this year, so the next year's tree ring will build upon what was already there, incorporating everything that was during the season and preparing for next year. That's what tree rings do. And they just do that in the most simple way. So we can still learn a huge amount of things and insights from nature that this just opens a box. For example, if you think about in mathematics and physics, they think about soap films as ideal shapes and so on and so forth. But then I asked myself, well, if you have, in physics, you have soap films and soap bubbles, and you have starfish like that, so nature must have done something in between. And I always ask myself this question, and then I find the answer. So indeed, shapes like this, almost spherical starfish, do exist. So, and they're optimal shapes in their own right. So they live in the Philippines, nowhere else, but Philippines is quite big. So nature is a fantastic experimenter, and throughout evolution has been doing that. For example, I also said the archetypical idea of snowflakes is this one, the dendritic ones. If you look at snowflakes, you will see everything there. But depending on the temperature and the humidity of the air, you can also have very irregular columns, or you can have columns, plates like that, also very regular. And these are images. So you see this is a capped column, so a column like this with a cap on top. So a bit like this, but then with a cap. So these things are very common and actually this is an image, and this is also an image of these things. And these are our shapes as a kind of, this is not a shape we make, but a shape that comes out of an optimization algorithm. And so for the first time now in physics, we can use these ideas. And again, it was initiated by a mathematician from Idaho, Bennett Palmer, and then I see natural shapes, I see the connections. So, but again, these are things that we need to figure out in the next 10, 20 years, if I may live so long. So. But anyway, then we can consider all these diatoms, all these flowers, all this fluid mechanics as a kind of optimization using a unified description. And that was really, that unified description did not exist before. So now the final part is, what will the future bring? So, you know, predictions are hard to make, especially about the future, but I'll try to see how I see it. First of all, this paper was from 2003. I called it a generic geometric transformation. generic for very, very generic, that unifies a wide range of natural and abstract shapes. And that title captured everything. So, as I said, we called it Superformula at that time. But it has been cited more than 600 times now. And what was interesting is biology, physics, psychology, applied sciences, antennas, nanotech. So there are more than 20 papers using it in nanotechnology. So you have in previous of these meetings, you have people talked about structural colors. We can make structural colors are made by small, very small shapes. They're not chemical colors. They break the light. And that's why using my shapes, my formula, they could figure out a whole range more things to do with nanotechnology. But they also used it in mechanics in design, vision and data mining. Data mining, for example, if you have a 20-dimensional space, what people do is try to cluster things into spheres or put a plane through it. That's all they can do. But we know there are starfish on the Earth. Why would there not be starfish in the 60th dimension? And if they do this, the starfish look like this, we will never find them with our technology of today. But we can find them with our technology. Again, forward-looking. So a lot of work is needed for the next years, but it's really fundamental. They teach it even in the first year in Harvard in mathematics things. They use it to optimize lasers and so on and so forth. Now, you ask yourself, why psychology? Just because people were asked in psychology, here you have a shape like this and a square and a sphere, which do you like most? But now you have all kinds of intermediate shapes. So people have been looking at, so you have an intermediate range of shapes, which do you like most? Not only visual, also haptic, so feeling. So, and this is many, many examples, but again, I have not said it, but it's really a quantification of what was qualitative before. So leaves were told elliptical, lanceolate, and so on. If I show this in the beginning to botanists and to mathematicians, yeah, they say it's round. Yeah, are you sure? Yeah, it's round. Huh? And then I showed them the supercircle and they said, well, oh, it's not round, it's really one of your shapes. So perception is very important. So we tend to, what we learned, if we learn something, and what I try to do in general is give people new glasses to look at things. And that's my goal. I'm not doing, I'm doing exciting things, but I'm not developing new laws of nature because I just want people to look differently. So in we had an exploration phase. I showed super graphics. Then we made sure that we could build an antenna company. We could make a scientific method. We built a broad scientific method. And now we're going to, in the third decade, we're going to do exciting stuff. And among this exciting stuff, oh, before that, so Thomas Kuhn is a philosopher of science, and 5 principles on models and theories: has to be accurate, yes, check. Has to be consistent, all spherical things are special cases, check. Broad scope, far beyond the bamboos, yes, check. Simple, brings order into all these different fields. And fruitful, should lead to new research directions, also check. Huh? So, from the very beginning, my goal was science, education, and technology. So, technology I need to make money, to stay alive and so on, and to do so, but a lot of people around the world are doing it in education and also in science. And this is just a kind of mind map. It's being used in CERN to process data. It's used in game technology, used in optics, used in printing, used in shape optimization, hydraulic solar cells. I'm not saying industrial uses, but you find scientific papers on this. I'm relying on scientific papers and patents. So first of all, with a continue better understanding of the world, we open the box and we see that the way we looked at nature is wrong. I mean, incomplete. Like I call it incomplete. Huh? So we have to look with different glasses, different lenses. New language. So as I said, forces in physics, distances, electricity, light, it's all circles and straight lines. Huh? But we tested, we don't find them. So in biology, we find few, if any, circles or ellipses. They're the exception. So we need a new language. We have the language, huh? So, but we just showed you the language, but it has to, it will take a few generations before it's really embedded everywhere, but it's used already all over the world, which is after 20 years not bad. Huh? So redefine complexity. So for designers, try to make a shape like this. First of all, it jumped out of our 3D Shape Explorer. And secondly, it's not more complex than a sphere. Not more complex than a sphere. Same complexity. Huh? Just imagine. So, and then I need to show if you can. So, Superformula waves and sounds. So now I'm going to waves. We do it in antennas, but sounds you can hear. And I think there's, oh, sorry. There is, no, there is a sound button on the presentation, but I don't see it here. So there's the few people that, yeah, maybe the colleague. No, okay, so there's, if you look at Superformula sounds, you have this kind of synth. Is the following question. So we studied 40,000 shapes. We don't find circles. Huh? And all the sounds are studied via circles, harmonics and boventonen and grondtonen, all circles. But is that the case? Maybe natural sounds are just super shapes. And that's what we're trying to investigate. But this is the synthesis part of waves and sounds. Huh? So synthesis. We're going to analysis and optimization in a later phase. That's a project that just started. This is what we have in current science, Boolean logic, black and white, mathematical language of patterns, but mathematics should also be a language of the unique. Every leaf on a tree is unique, and we can give it the right numbers to be unique. Entropy is generally the decay, and we're all the universe is going to die and so on. No, it's creativity and magic. Huh? So the micro versus quantum versus relativity theory. So we have to unify it. Huh? I think I'm always positive. I think I can do that, but in a very different way as all the physicists are trying to do. So and instead of decomposition, everything, we have to look at forms and shapes in their generality. So my latest project is, I think the whole circularity system and the heart is just one system. We know it's one system, but mathematically it's also one system. And it switches from a tubing system, a cylinder, and then it turns, and it switches to a Möbius band, and then you only have a one-sided. And that's the exchange function. So that's my new model of the heart and circular system, just holistic. And every, if I can prove that, and I think I can, then everything like complex ecosystems can be real one mathematical system with an inside and an outside, or just one-sided, whatever. So that's my goal for the next 10 years. So instead of thinking about division and classification, no. Unity and inclusiveness. So that's also something we have to. And number 6 is my greatest joy is working together with people. And these are, I work with most people now. I've been in mathematics for quite a while. The Chinese group that cuts all the leaves and measures everything. My mathematical friends, Bert, Diego, Ilya from Georgia, Paolo from Italy. Johan, a great talent, but he started his own restaurant, fortunately. And then a lot of other people that I work with. So, and then I live in Antwerp, but I have my company together with others in Tilburg. Antenna Company was a spin-off from that one. And our idea is an open innovation sim, so we have ideas. We kind of build a proof of concept, we kind of build a proof of business, and then attract money like this. So to build really a foundational strategy, you need lots of money. Huh? So that's, we want to tread very carefully. And maybe this is also with sound, maybe you can, that's the last slide. So.
Today, we present a radical new approach to 3D modeling. It can be used to create games, films, and animation. It is based on mathematics, physics, and natural growth. We call it natural procedural generation. There are different methods to create 3D environments. Modeling by hand gives great control, but is very labor-intensive. Standard procedural generation is fast, but lacks realism and control. That's why it's time to change the game, to enter a new era of simulated reality based on a revolutionary mathematical discovery. Natural procedural generation enables you to create completely unique, realistic, high-quality 3D environments. Since everything in our scenes is generated, it's ideal for fast creation with small file sizes. Since our tools are driven by mathematics, the generated environments are infinite. It's even possible to create infinite variations on trees, flowers, and other natural objects to enrich your scenes. In short, natural procedural generation is the perfect end-to-end solution for creating realistic natural environments. The game is already changing. Don't miss out.
So this was actually just a first prototype, but it's just a few lines of code, really. It's just a few. You don't need 3 developers working for 2 months to get it right. No. One developer developed this in half an hour or so. But again, this is very disruptive, so not easy to get it into the market. But we'll get there eventually anyway. So I would like to thank you for your attention. Yeah, if there are any questions. So actually I also have on that table, there are various natural shapes that you can see. So not only the images, but try and feel. I also have some of these books with me. If you want to look at it, they can look at it, and they're for sale too, if you wish. And again, thank you for your attention.
Thank you, Johan. Thank you for your presentation. And
so how long did I do? Oh.
Take some room for like 2 or 3 questions now, and leave the rest for at the bar. I'll check out where that is. We also have, and I have to take a sneak peek for that to finish my part up. People who want to stay for dinner and have a chat with Johan. There's a dish. I think it's 19 something, but it's close around to that. I didn't get the number. It's today it's Vongoli. If there are vegetarians who wish to join, let me know, and I'll take that down and notify the chef for that. So let's take 2 or 3 questions now and leave the rest for later. And Johan, if you would like to repeat the question as...
Yes, I will. Please. Yes.
I'm curious, in your formula, the n and the other parameters look like they're integers, but what happens when they get...
No, they're real. They can be real, or complex numbers or functions. Okay. Don't worry. So. Yes.
Yeah, so maybe I have an obvious question, because if I look at the formula, it's like Fourier transformation.
Well, actually, Fourier transformation is based on circles. Huh? But what we also have done in the recent years is actually if you have a circle, and you have, from the center you have a vector, and you project it, then you have the cosine and the sine. Yeah? And these are, so if you now take a supercircle, you can also have a vector and project it down, but then you will see that it remains one for a long time. And then it goes, so actually your wave will look like this. Yeah? If you have a square like this, your wave will look like this. Each of these shapes has their own trigonometric functions and has their own Pythagorean theorem and has their own Fourier analysis. So that's something we...
So also it links me to the same Fourier, it links me to the antenna, so the antenna analysis you also do, pass you did via Fourier. But if you look at the Schrödinger equation, you also have wave functions. So it's all about the sines and cosines, and in your formula, it looks like all these things come together in the formula.
Yes, but I didn't show this, but for example, if you think about, let's say, let's take a circle and a sine, and you make a sound of it, it looks like a tone on a flute, very pure. But if you would take, for example, a starfish, your sound would be very rich. Would be very rich, and it would be more like an organ. But if you put it through Fourier, you will have different frequencies put together. But in the terms of the super shape, or in terms of the starfish, it's only one sound, one pure sound. That's what we're trying to figure out.
So is that always an advantage? Because we found algorithms to very quickly calculate Fourier coefficients very efficiently.
I know, but I know, but yeah.
Price these complex shapes easy, but is it easy to find these?
Yeah, we just there's a paper in review where we have. It's not. So, for example, that's a very interesting question, because if you have smooth functions, that's easy to do. But if you have piecewise linear functions, it's stupid to do it with sines and cosines, because you also have the Gibbs phenomena, and people use it, but it's stupid. So if you use, for example, let's say the Fourier series or the trigonometric functions on a square, you can do piecewise linear, much easier than you do it with Fourier. But it's a continuum again. Fourier is one specific case, and we generalized it for any shape. But it's a pure mathematic. So, as a biologist, if I see all these shapes, they're not circles. We have to find another language. And since flowers and waves are the same, I expect that maybe we also need another language, or a richer language. Let's call it a richer language than just Fourier. Fourier works fine, and they have been using it for many years, but it's not ideal. So
these shapes you described, these are kind of minimal surfaces, like a circuit, but just a general.
Well, yeah. Well, you can.
Have something that breaks the symmetry, like the starfish is going in 5 directions, and then it's the minimal surface.
Well, that's two questions in one. First of all, the interesting thing about symmetry breaking. For example, if you have a starfish and you morph it back to a circle, and think about this m parameter, you can have a circle with m5. So you have a circle and it grows into a starfish, there's no symmetry breaking. So everybody thinks there's symmetry breaking.
No, it's just a 5-fold symmetry.
And the first question I forgot now, but so first part of the question was?
So the surfaces you show.
Minimal surfaces.
Minimal surfaces. So these are kind of the eigenvectors of this.
Yeah, this is there's a few papers on this. There's called anisotropic mean curvature surfaces. And normally spheres are mean curvature surfaces of constant mean curvature surfaces. But if you define your energy functional differently, according to a square or something, or then your corresponding minimal surfaces, like the Catanoid, would be something like the starfish that I showed. So, but it's well known. It's so this is all figured out already mathematically. So that's why I'm quite confident that it's also minimization.
So you can now, I try to rationalize, sorry for the so you can generate now eigenfunctions for specific problems and this makes it easier to describe this problem. So I need, let's say, more components in Fourier if I project it on the Fourier space than with this.
But for example, on a bit on another level, but we're going to submit a paper on using, let's say, super shapes as an example in quantum. Why? Because everything in quantum is based on isotropic spaces. How does a particle behave in in a circle? But what does it do in a square? How does it behave in a starfish? That's another matter. You have different eigenfrequencies, you have different eigenvalues. So that's all opening doors. Maybe Pandora's box, I don't know.
Okay, we'll leave it at that for here and jump on Johan in the other part of the room here.
Anyway, I hope you liked it. It took a little bit more than the allotted time, but it's a fascinating story. And once I start talking about it, so feel free. So I have a ResearchGate page, and all my presentations and papers are on there. So if you wish the scientific background.
Thank you.
Thank you.